right, good evening. And we're getting near the end here, getting to some real fun surfaces tonight called quadric surfaces. These are highly related to the conic sections that we saw before. They're going to help us to understand these. Conic sections were plane curves, right? Curves in the plane. Quadric surfaces are sort of the generalization of that, surfaces in free space. We'll say that there are 6 of these. And we'll do them one at a time using conic sections to figure out how to sketch them. So suppose we do this one first. The first one is the ellipsoid. This has standard equation. X squared over a squared plus y squared over b squared plus c squared over c squared equals 1. Call that equation 1. This ought to look like something that's similar, right? What does that look like? You've seen before. Well, it's kind of like equation for an ellipse, right? It's similar to x squared over a squared plus y squared over b squared equals 1. The ellipse. What was the ellipse? Remember, it was an oval. Looked like this. This was the standard equation for ellipse. If you wrote down an equation of this form, then it was centered at the origin, went out to plus minus a on the x-axis, plus or minus b on the y-axis. So this looks just like that with one more term for z. This was a plane curve, right? It only had variables x and y. This is a surface in free space. When you write down this one equation in the plane, it restricts you to a one-dimensional object, a curve in the plane. When you write down this equation, it reduces your dimension in 3 dimensions to 2 dimensions. You get a 2-dimensional surface in free space. Now, what in the world does it look like, right? We can get a good feel for it by doing what's called a trace. These include in the, let's say in the z equals 0 plane. What is a trace? It means you're going to intersect this surface with the plane and look at the curve that results, right? So we're going to look on the z equals 0 plane. If I put z equals 0 in this equation, I get, oh, there it is. That's the ellipse equation, right? X squared over a squared plus y squared over b squared equals 1 is the intersection of the xy plane, the z equals 0 plane, with the surface, whatever it looks like. So I can start drawing it now. There's x, y, oops, y, and z. And the idea is the xy plane, we already know how to draw this from doing the conic sections. It's like this. Oops, oh boy, I'm not getting this right. X, Y, and Z. Let me put it in the standard right-handed configuration here. X, Y, and Z. So X goes between plus and minus A. Y between plus and minus B. And all within this Z equals 0 plane. That's the idea. We're going to cut this surface, whatever it looks like, with the plane z equals 0, get this curve. Now I could try doing something else. I could try doing, say, the z equals 1 plane. I'll just move it up a little bit. What does that look like? Well, that's just one unit directly above this one. So I just slide up one unit. This plane, z equals 1, parallel to the z equals 0 plane. I can consider cutting this again. Now what I get, if I put z equals 1, I've got x squared over a squared plus y squared over b squared plus 1 squared over c squared equals 1. Wonder what kind of curve that is. Right? It's actually pretty easy. What I do is I subtract 1 over c squared from each side. Get x squared over a squared minus y squared over b squared equals 1 minus 1 over c squared. And here's a xy plane curve within this trace z equals 1. Right? Wonder what that is. I know what that is. I'll divide through by 1 minus 1 over c squared and write it equivalently as x squared over a hat squared plus y squared over b hat squared equals 1, where a hat, I've divided through by 1 minus 1 over c squared in this equation. So a hat squared is a squared times 1 minus 1 over c squared, and b hat squared is b squared times 1 minus 1 over c squared. In other words, I take this equation here, I divide it by 1 minus 1 over c squared and get 1 on the right, and then this becomes a squared times 1 minus 1 over c squared, that's a hat squared. This becomes, this divided by 1 minus 1 over c squared becomes b hat squared, which is b squared times 1 minus 1. But now that's an equation for ellipse, just with new smaller axes, a hat and b hat, where a hat is reduced from a by this factor square root 1 minus 1 over c squared, and b hat is reduced from b by the same factor square root 1 minus 1 over c squared. So you get a smaller ellipse up here. That with semi-axes, a hat. Well, this is already getting tedious. I've only done 2 traces. Machines are very good at this these days. If you get a software package like MATLAB, it will plot these things up, and it will do what's called a wire mesh diagram. You can plot a whole bunch of these planes. Maybe the z equals 1/2 plane, you get an ellipse that's in between these 2 sides. And you put a z equals minus 1, you get another ellipse down here. Here's z equals minus 1/2, maybe in here. And here's z equals minus 1/2. And you start to see this coming together. It's turning into sort of an oval. What we're getting back, we're getting something like this. That's what the ellipsoid looks like. It's this surface, and we can sketch its equator here. It's kind of like an oblong planet, right? Here's the backside. There is a rough sketch of the ellipsoid by making a whole bunch of those traces. Z equals 1 plane, z equals 1/2 plane, z equals 0.1 plane, a whole bunch of those. Make like wire mesh diagrams like you see computers make, and get a pretty good idea of what it looks like. Moreover, you can do traces the other directions too, right? We can also do the x equals 0 plane. I wonder what that looks like. Now I just put x equals 0 in this equation. Now I've got y squared over b squared plus z squared over c squared equals 1. I recognize immediately what that is. That's an ellipse with semi-axes b and c in the yz plane. So I recognize now, oh, that's this one right here. If I call this the x equals 0 plane, the plane of the board, oh, it's just this thing I drew right here. How about that? That is an ellipse with going up to c on the z-axis, down to minus c, and as we get surmised before, minus b to b in the y-axis. So there is that one, and similarly, I can do it in the y equals 0 plane. By saying y equals 0 in this equation, now I get x squared over a squared plus z squared over c squared equals 1. Recognize again an ellipse. All these things are ellipses. An ellipsoid gives you an ellipse, any particular, any of these three axes, any way you slice it. So now you can draw this without maybe such a jumble anymore. This is how we typically draw an ellipsoid. We'll draw the ellipsoid in the YZ plane, going up to C and out to B, minus B and down to minus C. And then we'll draw its equator like this, much like we draw a sphere. It's just we draw it kind of oval instead of circular for the cross section. And there's the picture we usually draw for an ellipsoid. I didn't draw this other one, by the way, this y equals 0 plane, the another color. It can get pretty messy if you try to draw too many of these, as you can see. Here's the y equals 0 plane, the XC plane of these two axes. And we've got an elliptical cross section there we're seeing like this. So you can draw all those and get an idea what it looks like, but usually it's simplest just to draw this. It's so cluttered. But all the cross sections there are ellipses. Questions on that one? That's the ellipsoid. This is actually a very important model. I used to work in the aerospace industry, and we did analysis of latitudes and longitudes and things. And do you know that in your GPS that's on your phone or anywhere else, they use an ellipsoid to determine the latitude and longitude. It's not like this. You might think the Earth is so spherical that we can just do this and take, if this is the equator across here, we can take the angle up here. If this is 45 degrees angle up from the equator, then that must be the latitude. That's called the geocentric latitude, this central angle. But actually what happens on an ellipsoid is this angle from the center isn't perpendicular to the surface. Instead, you take a perpendicular to the surface, this, and then go a tangent to the surface, I guess I should say, and the perpendicular to that, and you say that this angle is your geodetic latitude. This is how they actually measure latitudes, is by taking the tangent to the ellipsoid and the perpendicular to the ellipsoid and calculating the angle from horizontal up to the perpendicular to the ellipsoid. Otherwise, you will not get the correct latitude and longitude. All right, and these are used in planetary models. I've seen these for even for the oblong moons of Phobos that aren't all that elliptical. The best thing they fit them with that's mathematically simple is ellipsoids. But a lot of the planets, they have an ellipsoidal model, and they'll build latitudes and longitudes. And what you do then is you build a little terrain for mountains on top of this. But the Earth is not real spherical. It's pretty spherical, but it's not enough that you can get accurate latitudes and longitudes. They have to build an ellipsoid for the Earth, and then add a little terrain on top of that, and then you get pretty accurate latitudes, longitudes, and altitudes out of that model. Okay, so there's one application of the ellipsoid. It's a pretty good model for modeling planets. Well, that's just the first of 6 quadric surfaces. Second one, boy, this is going to be complicated, right? No, actually, these equations follow pretty simply from one to the next. It's not so hard to memorize because a lot of them are simpler. Let's do this one. Let's just do the exact same thing here. X squared over a squared plus y squared over b squared minus z squared over c squared equals y. I just change 1 plus to a minus. Oh, but it changes everything, right? And they say, now what do the cross sections look like? Let's look at these traces here. In the, let's look at the z equals 0 plane again. Z equals 0 plane has butt trace. I put z equals 0, and I get the same ellipse I did here. Though it's looking pretty similar so far. X squared over a squared plus y squared over b squared equals 1. That's an ellipse. So again, the cross sections are ellipses. It's an ellipse in the xy plane. And actually, if you put z equal to any constant, you find you again get ellipses. All the cross sections z equals a constant are ellipses, like they were here. You can do some more of these, right? It just gets tedious. How about, let's try something else though. Let's try again the x equals 0 plane of the board here, the yz plane. This has, well, let's say x squared over a squared minus c squared, right? We just put y, I'm sorry, x equals 0. We put y squared over b squared minus c squared over c squared equals 1 because x equals 0, this falls out. And within the x equals 0 plane, now we got a hyperbola, right? With semi-axis, with constants b and c in here. So the distance from the center of the vertex, for instance, will be b. And then might say, well, what happens now if we put y equals 0, y equals 0 plane? As well, I put this equals 0, I get x squared over a squared minus c squared over c squared equals 1. I observe once again it's a hyperbola. So the cross sections, instead of being ellipses, ellipses, ellipses in the three different directions, are ellipses, hyperbolas, hyperbolas. And you can try and sketch some of these. Right? The idea is that a, b, and c are just given numbers, positive numbers. So in the xy plane, I get this elliptical cross section going out to a on the x-axis and b on the y-axis. But now, actually, if you go at the higher traces, you put z equals 1, for instance, you'll actually get bigger ellipses, like this. And if you go down to lower values of c and intersect it, z equals a negative number, you will also get bigger ellipses. Then in the yz plane, you get cross sections that are hyperbolas. And also in the xt plane, right, the xt axis, you follow that, you can get hyperbolic traces in that. These are often not drawn because the drawing starts to look cluttered. But here is the second one, we call it a hyperboloid of one sheet. Now you can see also that these names give you a hint what it looks like. The ellipsoid, all the cross sections are ellipses. Hyperboloid of one sheet, lots of hyperbolas, right? Hyperbolas in two directions and ellipses in the other direction. So this will be the second one, equation 2. This is the standard form of the equation. This doesn't, this puts the center at the origin and orients it up this way. We'll talk about how to orient it other directions later. Just like the conic sections, you can actually rotate these things around in different directions. But you'll see these things used occasionally in real life. There's a hyperboloid of one sheet, and it comes just by taking the ellipsoid equation, changing plus to minus in one spot. All right, let's look at number 3. The standard equation for next one is z squared over c squared minus x squared over a squared minus y squared over b squared. Now it's just about that, like that equation, but now I've got two minuses. You put two minuses in the ellipsoid equation. We like to keep the plus on c this time. It's for standard way of drawing it, but you don't have to. Whenever in the ellipsoid equation you change two of the pluses to minuses, you'll get this figure that's called a hyperboloid of two sheets. We need to do some specific examples here in a moment, but let's just say here's the equation 3. And what happens here is if you do traces and intersections of this figure with, if I put the z equals 0 plane, oh, I got nothing. I got negative this equals positive. Impossible, right? I can't make two non-positive numbers sum to be equal to positive, so there's no solution. Empty trace, right? But if I were to put equals c. Then I get c squared of c squared is 1 minus x squared over a squared minus y squared over b squared equals 1. These cancel. Now I've got minus x squared over a squared minus y squared over b squared equals 0. Says that there's only one point of solution, right? This is a non-positive term. This is a non-positive term to add up to 0 that's left. These have to both be 0. It says that x has to be 0 and y has to be 0. You got only x equals 0, y equals 0, z equals c. And the same thing when you put z equals minus c, you get right, the same thing. This will be 1 here. You'll get only the origin again. Now, if you put z equals a bigger number, then you can start to get ellipses again. Z equals, let's say, square root 2c. Then this becomes square root 2 squared. This becomes 2c squared over c squared is 2 minus x squared over a squared minus y squared over b squared. 1, if you subtract 1 across and add those across, you get equivalently 1 equals x squared over a squared plus y squared over b squared. And you observe now it's an ellipse. So cross sections are ellipses once you get far enough up. And also z equals plus minus square root 2c is the same cross section. Plugging in, you get 2c squared over c squared here. And so now in the other directions, you notice that if you put in x equals 0 plane, then this falls out. You've got z squared over c squared minus y squared over b squared equals 1, which is a hyperbola. Right? Just looks like x squared over a squared minus y squared over b squared equals 1, just in the yz plane instead of the xy plane. So hyperbola. So what we're observing is when we make traces of these quadric surfaces, we consistently get conic sections or no solution or a degenerate case. Now all those things we learned about conic sections that come into play to help us to draw these now. I know we still have to do specific examples. Well, once again, if I put y equals 0, what I get? This term falls out, and I got z squared over c squared minus x squared over a squared equals 1. Again, a hyperbola. So the cross sections of the hyperbola at 2 sheets are again ellipses, hyperbolas, and hyperbolas, but it's oriented a little differently. Here's what it looks like. Here's the cross section within the plane. Z equals square root 2c is the ellipse with semi-axes A, B. And same thing down here within the plane Z equals minus 2 square root 2c. You get an ellipse with semi-axes A and B. And in the middle, here's the c equals 0 plane. We got no solution. And the other directions we'll get hyperbolas, right? And that's these other curves. This is a hyperbola, one branch of it. This is a branch of a hyperbola. So is this within the xc plane, and this one within the x plane. But we draw it like this. We don't usually draw these green lines the other direction. And just do that to show you what the traces are. There's a hyperbola of 2 sheets in its standard equation. Like that, it's 2 sheets. Right? But the cross sections, once again, are conic sections. So let's finally get to an example, see how this helps us to sketch. If you can memorize those things, they're standard equations, then you can do things like this. Suppose I said example, sketch the graph of x equals, x squared minus y squared minus z squared equals 4. I wonder what that looks like. Lots of these equations that have squares and first powers of x, y, and z actually convert into these quadric surfaces. We're going to show the general equation coming up. Any questions so far? It's a lot of stuff. Right. What you can do when you see this, it's not in standard form, you put it in standard form. That looks just about like this. I'm going to divide it through by 4 and rewrite this as x squared over 2 squared minus y squared over 2 squared minus z squared over 2 squared equals 1. And I recognize a hyperboloid of 2 sheets. Except, wait a minute, x is first and y and z are second. That's not a problem. The idea is, that's the standard equation to see it drawn like that. But if I put x as the positive term and y and z as the negative terms, it simply means it's exactly the same picture with the axes interchanged. It opens about the, since this one opened about the z-axis, when I put z as the positive term, this one must open about the x-axis, but exactly the same picture. Sketch it like this. Hyperboloid of 2 sheets having hyperbolas opening this way and this way. And then elliptical cross sections this way. The back one. It's like a translucent figure. This one over here like this. And remember so probably these points here, we said you have the point 0, 0 plus or minus c. So this must be 0, 0, c. This must be 0, 0 minus c. So you see how you get these important points in cross section sketch. That means this thing is 0, 0, c, whatever is underneath x. This must be the point. Do this the wrong way. I drew it around the about that. Again, it opens about the x-axis, which is this one, well, standard. So it opens at 2, 0, 0, 2 along the x-axis. Whatever divides x instead of over here, whatever divides z from the origin of z. So 2, 0, 0 and minus 2, 0, 0. And then this has to come out. The elliptical cross sections this way. That with elliptical cross sections this way. Goes in those two directions. There it is. There is the hyperboloid of 2 sheets. That is the sketch of this one. Now, how do we make this more accurate? One thing to recognize is actually when go back and look at here, what happens if A equals B? So this cross section here actually degenerates to a circle, right? You can rewrite this as x squared plus y squared equals a squared. It's a circle of radius a when these two are equal from the negative terms. That's what's happened here. These two are equal. And so actually these cross sections I call ellipses or circles. And we can sketch a couple of those to make this more accurate. Let's go and sketch it in an easy trace. What you do is you recognize it's supposed to look like this, and then you fill in a few numbers to make it more accurate. That's the idea. Memorize this picture, turn the axes the right way, make a couple easy traces. Like what would be a good trace here? You get a nice circle in this plane. Well, if I were to put, let's see, let's put x equal 2. X equals 2. So the x equals 2 plane, what do I get? Well, I put in 2 for x in the equation here, or up here. This gives 2 squared minus y squared minus z squared. Oops, not x equals 2, that was this one. Sorry, x equals 4. X equals 4. So it's 4 squared minus y squared minus z squared equals 4. And this becomes y squared plus z squared 12, which is square root 3 squared. X squared plus y squared equals a number squared is a circle of radius, in this case 2 square root 3. So what I can do is go within this x equals 4 plane I surveyed. X equals 2 is what you do. So I get a circle of radius 2 square root 3. 2 square root 3. So now you put a little teeth into it. At x equals 4, at x equals 2, it just touches the x-axis there. At x equals 4, twice as far out, you get this circle of radius 2 squared. So that's how you tend to draw these things. Is remember the standard equation, rotate it according to which variable comes first in this equation, and then plot a couple of traces. Another good trace to do once you've done x equals 4 is try this one, x equals minus 4, because actually get the same equation, right? I put x equals minus 4 in here, I got minus 4 squared is the same as 4 squared, minus y squared minus z squared equals 4. I'll get exactly the same equation on the same circle just within this plane x equals minus 4. So there's that symmetry. The two sheets of the hyperboloid having corresponding cross sections. There's how to actually draw one. Well, suppose I gave you this one then. Suppose I said sketch x minus 2 squared over 2 squared plus y minus 1 squared over 4 squared plus z squared. Wonder what that looks like. A lot of the problems in here are just learning to sketch these things. So what does this look like? Well, if you think about it, if you just get rid of this minus 2 and minus 1, you've got an ellipsoid, right? It's x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. Unlike the ellipse, a does not have to go under x, or under the, does not have to be the biggest number, I should say, right? In the ellipse, you always made a the biggest number, the semi-major axis. Here, a, b, and c, a goes under x, b goes under y, and c goes under z. It doesn't matter which one is biggest. So this is actually an ellipsoid, except I replaced x by x minus 2 and y by y minus 1. Well, remember, for any equation, if you, in any dimensions, if you replace a variable by that variable minus a number everywhere, that just shifts the graph over. So this is exactly the ellipsoid, but instead of being at 0, it's at whatever you subtract here, 2, 1, 0. It's what you subtract, because now if x is two units bigger than in the standard equation, right? The standard equation would be x squared over 2 squared plus y squared over 4 squared plus z squared over 1 squared this way. Semi-axis lengths 2, 4, and 1, so we could sketch this one in standard configuration, x going out to 2, y going out to 4, so you get this cross section for the equator in the xy plane, going between plus and minus 4 and y, plus and minus 2 and x, and then z going between plus and minus 1, right? So it goes like that, and so you get this kind of elongated ellipse like that. Cross section's missing. Try it one more time. It doesn't look pretty. So it goes out to 4 and minus 4 and z, 2 and minus 2 and x, and then it comes just up to z equals 1 and down to z equals minus 1. I should draw this equator dotted back here so it looks like. And there we go. There's the ellipsoid here. How is this one different? If I replace x by x minus 2 and y by y minus 1, it just moves it 2 units in the x direction, 1 unit in the y direction. I just have to put in x 2 units bigger to square the same number I did here. Y 1 unit bigger over here to square the same number I did here. So the same points will satisfy here that satisfied here if I just make except that x has to be 2 units bigger and y has to be 1 unit bigger. So now we just draw that same thing, but we put it at 2, 1, 0. So I got 2 in the x direction, 1 in the y direction, and here's in the xy plane, this point here. 2, 1, 0. I draw exactly the same shape. Centered here, I go over 4, 1, 2, 3, 4. I go 2 in the y direction, so I get this kind of equator. Make it dotted because it's going to be back. Pointing in the z direction. I draw exactly this picture, just shift it over so that the center is at 2, 1, 0, and that's it. So you can reorient the figure by putting a different term, positive term. You can also shift it over by replacing any variable by that variable minus its number. Right. Getting the hang of it, maybe. I want you to be able to do this for the next test. As I said, x squared minus y squared plus z squared equals 1. What's that? That's actually a hyperbola of one sheet, right? Because it looks like x squared over a squared, thinking of it this way, x squared over 1 squared minus y squared over 1 squared plus z squared over 1 squared equals 1 is a hyperbola of one sheet. Since the y term is negative instead of the z in equation 2, that means this is going to open about the y-axis instead of the z-axis, right? It's the standard equation just with the y term negative. So it must look like this. Spool we saw before. There it is, something like that. For your sketches, I don't expect you to be elaborate. The idea is to draw a simple trace or two. Maybe if I intersect this out here, the y equals 1 plane. What's in the y equals 1 plane? What's the trace? I put y equals 1 and I get 1 here. And so I got x squared minus 1 plus z squared equals 1. It tells me x squared plus z squared equals 2. Oh, it's a circle. Square root 2. Once again, elliptical cross sections that you typically get degenerate into circles because the coefficient under x and z were the same, right? So this is the circle of radius square root 2. I can go up square root 2 here, up square root 2 here. That gives a pretty accurate trace. Similarly, it's not just a y equals 1, y equals minus 1 squared gives you the same equation here. And so over in this plane here, y equals minus 1, we can draw a corresponding trace. Also with axes, square root 2. Those are circular cross sections. And you can draw a thing like, I think it's nice when you draw this hyperbola of one sheet to draw its waistline here. It's always nice to draw the y equals 0 cross section when it's centered at 0. Y equals 0 gives us, let's see, x squared plus z squared equals 1. Oh, it's a unit circle. How about that? So the waistline of this thing is the unit circle, comes out 1 unit on the x-axis, 1 unit on the z-axis. It's always nice to draw these things that are around the origin. People look for that to be accurate. And here's your unit circle at the origin, circles of radius square root 2 out of y equals plus or minus 1. This arc line axis. Some good examples, really. That shows you the power of just memorizing these 6 common quadratic surfaces. Well, there's some more to go still. They aren't too bad because, once again, they're somewhat similar. The fourth one will be the elliptic paraboloid. This one has standard equation. Z equals x squared over a squared plus y squared over b squared. There is a little bit of variation in these from book to book. You'll find actually these last 3. I think this is the way your book puts it. You might look at Wikipedia. There's some beautiful pictures there I want to put up. Maybe I'll put them up next time. We can do some of these ourselves. For instance, have you ever seen this one? I took 2 peanut butter jar lids and I strung some stretchy string between them. And if you were to take this thing and twist it, right, you get an ellipse, a hyperboloid of 1 sheet. It's a nice hyperboloid of 1 sheet, which shows actually that the hyperboloid of 1 sheet, since you see these strings are straight lines, is what we call a lineal surface. You can generate the surface by drawing infinitely many lines, lines only. So a surface generated just by lines like this one, hyperboloid of 1 sheet, is a lineal surface. But those things come up in a lot of surprising ways, right? All right, there's a neat science experiment at the museum actually where they draw a curve like this, or they cut a curve like this in a big piece of wood. And then they have a pole here with a long, straight bar at the end of it. And when they spin this pole around, the straight bar at the end of the pole goes right through this curved surface. How can that be? Well, they put it in a special angle so that it's like the lines on that hyperboloid of 1 sheet. If you were to continue this on, it'd be one of the lines on a hyperboloid of 1 sheet. And so every time it rotates around, it's actually generating part of that hyperboloid. This is a hyperbola branch here, and this is one of the stretchy strings. It's just sliding through there. It looks like it can never go through the curve, but as it moves around, it slides straight through that curve because it's a hyperbola. But yeah, I guess that this thing rotates around and around here. Flat board with the cutout in it. Or go straight through there without touching it. Quite a good experiment. Then there's another one over here, but come back. So it goes through the 2 bars. Or maybe there's no board over there. All right, so interesting examples you can come up with. What those things can do. Here's the next one. This one doesn't look too different from the others, right? It said x squared over a squared plus y squared over b squared plus z squared over c squared equals 1. You get z equals this. So it's a little different, but not extremely. Now, if you do the cross sections again, you put z equals 1. Then you get 1 equals x squared over a squared plus y squared over b squared. Obviously, an ellipse, since it's the standard equation for it. And if you put z equals any other positive number, you also get. So you get elliptical cross sections in that direction. Then you put like x equals 0, and you notice you get this trace, c equals y squared over b squared. Well, that's just a parabola, right? If you put y equals 0, you get z equals x squared over a squared. So these are parabolas, hence the name elliptic paraboloid. That really helps you to figure these things out. You can memorize the equation. Notice it has cross sections that are ellipses and parabolas. It must be ductile and elliptic paraboloid, right? If it walks like a duck and backs like a duck, I don't like that. It's got to be a duck, swims like a duck. And so, similar here, if it's got ellipses and parabolas, it must be elliptic paraboloid. Right? So, this one, if you try and draw those things, it's like this. In the plane, d equals 1 we just showed, you get an ellipse with semi-axes A in the x direction, the y direction. So here it is. It's this goes up like this forever. So it goes up forever. But parabolic cross sections here, parabola, and this elliptic cross sections here. That's an important one also. Just like when you have 4 conic sections, there are going to be 6 quadric surfaces. Or 5 is going to be z squared equals x squared over a squared plus y squared over b squared. If you just change z to z squared here, you get this one that's called an elliptic cone. If you put z equals a number, like put z equals 1, you get x squared over a squared plus y squared over b squared. An ellipse, put z equals 2, you get a bigger ellipse. But let's put z equals 2 or something. 2 equals x squared over a squared plus y squared over b squared. When you recognize this ellipse, you divide by 2 and put 1 equals x squared over a hat squared plus y squared over b hat squared, where a hat is square root 2a, hat is square root 2b. You're just getting an ellipse with larger semi-major and semi-minor axes. And then you can do in the other direction, right? You put, let's say, x equals 0. Now, what do you get? This falls out. You got z squared equals y squared over b squared. What does that mean? Not too bad. You just square root it and say this is really z equals plus or minus y over b, right? It's 2 lines to the origin. YZ plane is slope plus or minus 1 over b. Similarly, if you put y equals 0, you got z squared equals x squared over a squared is again 2 lines. This time z equals plus or minus x over a, also lines to the origin. Sketch this one then. It's this thing that looks like an hourglass. Got elliptical cross sections this way. The only thing is the cross sections can be ellipses instead of circles. Here is your elliptic cone. As this standard equation. It's very similar, right? Finally, one last one. This is the hardest one of all by how much students. Fortunately, in Oklahoma, we can actually draw this one. Every problem knows what that will look like. All right, so we look at z. It looks just like the elliptic cone, except I changed the plus to minus. Z equals x squared over a squared minus y squared over b squared. And it changes it around, right? This is an elliptic, hyperbolic parabola. Take the elliptic parabola and change the plus to minus opposite. From equation 4, it's 4. This is 6. 6th one. This is 4 with a minus instead of plus. So this is hyperbolic parabola, right? And you guess why the cross sections are hyperbolas of parabolas. I put z equals a number, z equals 1 is the easiest. I get 1 equals x squared over a squared minus y squared b squared. I said, oh, that's a hyperbola, right? I can get other hyperbolas by putting z equals different numbers. If I put x equals 0, then I get, let's see, z equals minus y squared over b squared. This is a parabola down. But if I put y equals 0, I get z equals x squared over a squared, a parabola up. How am I going to draw this thing? This is how it draws as a saddle, where you sit down on the origin. Looks like this. Of course, you can do better than this because they have computer graphics, but in the x equals 0 plane of the board, you get parabolas down, and if you put x equal other numbers, you get other parabolas down. I just did a few of these here. What you wind up with is this kind of a situation. This parabola is down when you're in the YZ plane or parallel to it, x equals 0 or a different number. Now this goes down here, the origin, and then comes back up here. Then it looks like this. There it is. It's a saddle. Painting the origin right because 0, 0, 0 is a solution. But you sit down on the z-axis under the origin, and there's your saddle. This is a parabola down. This one is a parabola up. This one on the backside, hyperbola. So that's the way it works, and you can sketch that one. So for instance, suppose I asked you to do this, sketch just the easiest case here. Z equals y squared minus x squared. Well, wait a minute, that doesn't quite look like this, right? Now the y is positive and the x is negative. What does that mean? It means you have to interchange the x and y axes. So this is a hyperbolic paraboloid, but turn the other way so that it's down around the y-axis and up around the x-axis. X, y interchanged 6. So it turns the other way. That means all I have to do to sketch this thing, roughly, to draw a saddle, put it down in this direction, sit down on the origin like that. There it is. And then you can make a couple of cross sections like you put in the y equals 1 trace. Now you've got z equals minus x squared. So in the y equals 1 plane, maybe it's out here, and y equals 1. This is the curve z equals minus x squared. I should draw it a little different. No, that's 1 minus x squared. 1 minus x squared. That's what this parabola is right here. And also, if I put y equals minus 1, I get the same equation, right? I get z equals 1 minus x squared. So it's also true in this corresponding plane right here, y equals minus 1. This same equation holds. It's that parabola too. So you can sketch a couple of those and make it a little more accurate. We don't have to go into a lot of detail. But that means that this is at 1 on the z-axis, for instance. X equals 0. Okay, there they are in all their glory. Quadric surfaces. There's 6 of them. And then we have this following very interesting note, right? You recall that any equation of the form ax squared plus bxy plus cy squared plus dx plus ey plus f in the plane equals 0 was a conic section. All we had to do to sketch it was we could rotate it and complete the square. I'll be able to sketch it. Like you could put it into one of the standard forms. Well, I said it's a conic section. It can be a degenerate case of no solution. But in any case, you can rotate it and complete the square to get a standard form or no solution or degenerate case and sketch it. This, in some sense, is the simplest equation after a linear equation, right? A linear equation is ax plus by plus c equals 0, first order powers of x and y was the general form of an equation for a line if you allow second powers, including this cross term, conic section, the degenerate case, or parabola. Wow, these things are important, right? They're kind of the next simplest equation after lines. We can do a completely analogous thing now with quadric surfaces in 3 dimensions, right? This is all in a plane. In 3D, if I write ax squared plus bxy plus cy squared plus dxz plus ez squared plus f yz plus, and we've got might get a bunch more terms here, but we have all first and second power possibilities. Gx plus hi y plus iz plus j equals 0. I just don't know a constant, and that's square root of -1 here. This one is a quadric surface. So a general second order equation here, well, these is a quadric surface, sometimes it's called a quadric. A degenerate case or no solution. Degenerate cases can be things like this. If I put all these higher power terms here and just write this left, if I put a through f equals 0, what is this that's left? X plus by plus cz plus d equals 0. It's a plane. So a plane is a degenerate case, for instance. And that also points out that 3 dimensions, a linear equation, a number times x plus a number times y plus a number times c plus a number equals 0 is called a linear equation of 3 variables where you have first powers and a constant. That was the general equation for a plane with a, b, and c nodes. That's what you get when you allow only first power terms. If you allow second power terms, the next simplest thing is a quadric surface. How about that? So quadric surfaces are the 3-dimensional analogy to conic sections of the plane. Once again, in order to observe it, what you do is you rotate it and translate it by rotating and completing the square to translate it. This time, though, you have to rotate in 3 different directions. Rotate the xz plane, the yz plane, and the yx plane. So rotating in 3 dimensions and completing squares. We can sketch it because we'll get one of the standard equations or degenerate case of no solution. So by rotating in 3 dimensions and completing the square to see what the shift is. These can be sketched because they can be reduced to their standard forms. So that's the analogy. Pretty neat. A lot of these come up in real applications. Well, let's try one thing. We are not going to do the rotations in 3 dimensions. The idea in this class is you learn rotations in the plane, and in higher mathematics courses, once in a while you have to do rotations in 3 dimensions. You just have to rotate in all 3 planes, but it's the same kind of equations. You might see if you take linear algebra, for instance. Physics classes need to do this too for their rotational dynamics. So we won't do that, but let's do the translation just quickly. Let's try this one. Let's translate the sketch. Now, what you do with the rotations are to get rid of these cross terms with the xy, the xc, and the yz. You rotate it 3 times to get rid of those cross terms, and then the remaining part you can complete the square. So let's try this one. There we go. Suppose I give you the equation for the final exam, z squared equals 4x squared plus y squared, no cross terms, right? Plus 8x minus 2y plus 4. The cross terms, there's no rotations necessarily. We simply complete the square to see how we have to translate it. So let's do that part. What do? Well, I subtract the 4z over here, and I'll write this as z squared minus 4z equals, and I'll combine the x terms. 4x, let's back to the 4 out here. 4 times x squared plus 2x, right? Back to the coefficient of x squared out and group all the x terms. There's 4x squared, there's 8x, right? And then 1 times y squared minus 2y. So subtract the 4z over and collect these like terms like the y and z. And now what you ask is, what do I need to do to complete the square in each of these variables? Well, I take 1/2 of this coefficient, recall, square it. I get 4. I need to add 4 over here. So z squared minus 4z, 4 makes a perfect square here. And then over here, I've got 4 times x squared plus 2x. 1/2 of this number squared is 1. So I need plus 1 here to make a square. And let's see, over here, so I need to get to make a perfect square here, I have y squared minus 2y plus 1. And let's see, I added 4 to the left, I added 4, 5 to the right, so I need one more here. Balance the equation. So now I've added 5 to the left and 5 to the right. Right? What do we have here? These are all equivalent equations. This is z minus 2 squared is this part, all plus 1, equals 4 times x plus 1 squared plus y minus 1 squared. That'd be, well, I subtract the z minus 2 squared over, and I can rewrite it in this form. Well, actually, let's subtract this over and subtract these over. Rewrite it as 4 times x plus 1 squared plus y minus 1 squared minus z plus minus 2 squared equals 1. I can rearrange them like that by algebra. What am I trying to do with this? Well, I'm trying to get it in standard form with a translation. So I'm going to rewrite this now as x plus 1 squared over half squared. 1 over half squared is 4. Plus y minus 1 squared over 1 squared minus e minus 2 squared over 1 squared equals 1. And there we go. Here is the standard form for a hyperbola of one sheet. Just with the translation. X replaced by x plus 1 shifts at minus 1 in x. Y replaced by minus 1 shifts at plus 1 in y. Here's a shift of plus 2 in z. So it's a hyperbola of one sheet because there's one minus, right? An x squared term, a y squared term, and a minus a z squared term. And what's more, since the z is negative, this is the standard configuration where it opens about the z axis. So it's hyperbola one sheet opening upward because the z term is the -1. Going back, this is by equation 2, the one for hyperbola one sheet, but shifted, right? -1 in x, 1 in y, and 2 in z. Center, instead of being at the origin, is going to be at -1, 1, 2. Try that. -1 in x, 1 in y, and 2 in z. So I'll draw this rectangular box. Do this. This point at the far corner of the rectangular box will be the point -1, 2. That's the center of a hyperbola. Now I can see that it's equator when I put the center on here. The semi axes are 1/2 and 2 for the 1/2 and 1 for the ellipse. So from here, I'm going to go out 1/2 in the x direction to here, but 1 in the y direction to be over here and over here, and draw this kind of an ellipse as the equator. And it's going to open like this. We could draw a couple more traces and make this more accurate. I don't really care about that. I want to know that you can draw this general shape. Maybe draw the equator and draw the center. All right. So there it is. There's a sketch of that one. That's the hardest problem in the section. Right. Complete the square. Recognize the equation of a standard equation with a shift. That's it. Hey. All right. So we'll do some of those for homework now. Well, I want to start the next topic, although I won't get very far. As you might guess, some of these things are a little easier to write their equations in other coordinate systems. What we want to now discuss, we had a radial symmetry in the plane, we switched to polar coordinates, right? What can we do in 3 dimensions? Well, this is going to be other coordinates in 3D. What do those look like? Well, there's very exotic coordinates, and you get to talk about it in more detail in calculus 4. Actually, we can do very general coordinates. But the ones that come up most often are when you have a radial symmetry in x and y. And there's just 2 systems for that. One of them is cylindrical coordinates, and these are very easy. They're just polar coordinates add z. Just about what they are. And then the other one is going to be spherical coordinates. Those are very useful. So we'll just do 2 coordinate systems in 3D that come up the most often, and we'll say they're more exotic systems to learn a little bit about in calculus 4. There are parabolic coordinate systems and hyperbolic coordinate systems. Cylindrical coordinates are this in 3 dimensions. What you do is you take any point, you drop a perpendicular down to the xy plane. Call that distance to the plane z. When you draw this line segment within the xyz plane back to the origin, call that distance r. Then take the angle counterclockwise from the x-axis to that line segment and call that theta. And you may have surmised already, right? This is just polar coordinates in the xy plane as z. That's all they are. In this system, you would say r equals square root x squared plus y squared. Therefore, and tangent theta equals y over x, just like polar coordinates. And then c equals z. Transforms from x, y, z system to r theta z system, cylindrical coordinates. And you label it with an order triple r theta z in that order. Identifies a unique point for each r theta z you put. There is one difference from polar coordinates, however. In polar coordinates, you put r squared equals x squared plus y squared because you also wanted to allow r to be negative, right? To get this 0.11, for instance, in polar coordinates, you could go around to the angle 5 pi over 4, the opposite direction, let r equal minus square root 2, right? Minus the distance. So the point could be described by minus square root 2, 5 pi over 4 with r negative, or you could call it square root 2 pi over 4, and both these polar coordinate pairs, one with r positive, one with r negative, give you that point. Then you can add 2k pi to theta and get other coordinates. But you allowed r to be negative, not so in cylindrical coordinates, because we're going to have integration problems if we allow r to be negative later. It just causes too much headache. We just restrict cylindrical coordinates for r to be non-negative only. So that's the one deviation from polar coordinates. We don't allow negative r. Cylindrical. Even easier than polar coordinates, right? You don't have to allow r to be negative. But now see. That's cylindrical coordinates. So let's try an example for that one. And I think you'll see how easy this is. We also need to convert these the other way. As you might guess, since in the xy plane it's just polar coordinates, once again, x is r cosine theta. You can drop the perpendicular here, right? Drop the perpendicular here. Since this is r, this length here, and this is theta, this side has to be, coordinate is r cosine theta, right? So that this over this is cosine theta. The y coordinate has to be r sine theta. So that this over this, r sine theta over r gets sine theta. So any triangle that's true, right? If this is r, then this is r cosine theta, this is r sine theta. And trigonometry. So those equations all carry over also. R cosine theta, r sine theta, c equals c, converts back the other direction. We call these equations 7, 8, convert between cylindrical and rectangular coordinates. Pretty easy since it's polar coordinates and has solution. Example. Let's convert the point in 3 dimensions. Minus 2 square root 3 to 4 to cylindrical coordinates if these are rectangular. What do we do? Easiest can be because we already did polar coordinates. This is r and theta. And so we say, this is x and y we can use to find r and theta. We say r is just by plugging in square root of x squared plus y squared, right? By 7. Your pimps. Most of the do it again. So this is square root of 12 plus 4, square root of 16 is 4. So you're exactly 4 units xy plane. Tangent theta equals y over x is 2 over minus 2 square root of 3. Here's where some people on the fence have some problems. They might say, well, theta must be the arctangent of minus 1 over square root. Actually, it's the arctangent plus pi. It's in the opposite quadrant this time. When we draw the unit circle, and there are 2 angles. If you think of this as minus a half over square root 3 over 2, or it could be plus a half over minus square root 3 over 2. Either would give this ratio on the unit circle. You can have y as minus a half, x is square root 3 over 2. This point, this angle, or you could have this opposite angle, plus a half, minus square root 3 over 2. Which one do we want? Well, x is negative and y is positive. We want this one. We don't want the arctangent. We want this angle, which is 5 pi over 6 of x. Right? This is a 30, 60, 90 triangle. 1 half, square root 3 over 2 and 1. Pi over 6 here makes this 5 pi over 6. What we have then is r is 4, theta is 5 pi over 6, and z we just copy. It's 4. That's how easy it is. It's just polar coordinates with z. We'll do some more of these next time because we're out of time. Let me get the homework done. Let's see. I won't give you on the cylindrical coordinates because we're going to do some more coordinates with it next time. The spherical. But out of 11.7, quadric surfaces. Try all these and bring some questions if you have them. 7. Can't read my writing. 15 to 39 odds. Put 41, so 15 to 41. Try those. Oh, it's just 15 to 39. I'm looking at the other one. Sorry, I've got 4 lines. 9 and 15 through 39 odds. That's it. See you next time.